Hi, in this video we will learn about the relation between the moments about mean and the moments about arbitrary point. We have learned in the previous session that the rth moment about mean can be written like this, that mr equal to 1 by n summation of I equal to 1 to n fi dot xi minus x bar raised to r. Now this m with suffix r will signify that this moment is of order r, and there is no dashed here. That will indicate that the moment is about mean. On the right hand side, you are going for the summation of fi dot the deviation of xi's from mean, right? Now this is a group data because the frequency fi is there with every xi, right? Now this will work for ungrouped data also, where frequency will not be there. There will be simply xi minus x bar. Clear? Now this r, this power here, may be 0, maybe 1, maybe 2, maybe 3 like that. Just like our previous session, our interest will be the value of r to be up to 4. Okay? Now we insert this a inside this expression. Then it will be looking like this, xi minus a plus a minus x bar. Now why we are doing like this? Because we are trying to find out the relation between the moment about mean on the left hand side with the moment about arbitrary point on the right hand side. Since arbitrary point is concerned here, we introduce this arbitrary point inside this expression, right? Now we rearrange and group it within brackets, so it will look like this, xi minus a, this is one part, minus the second part is x bar minus a. You write in front this minus here and just turn it up and it will go like this. Okay. Now we call this equation as equation 1, that is mr equal to this part. Okay. Now this xi minus a is a deviation, is the ith deviation, and we name this ith deviation as di. So we write like this, di equal to xi minus a. Now what is our intention? Actually our intention is to link this one with m1 dashed. That means moment about arbitrary point of order 1. So let's see how we can do that. You rearrange this part so that xi comes to the left hand side and a plus di goes to the right hand side. Okay. Now if you look at this figure, this part, this di, a and xi will be looking like this. A is here and xi is here. What is the meaning of this? Your arbitrary point A is actually a deviation from the origin 0, and all xi's are deviations from the origin 0, right? Now this di is actually the difference between the xi's deviation and the a's deviation, and it will be looking like this, right? So you can see that xi is actually a plus di. So this a's deviation plus di's deviation will give you xi's deviation, right? So we take the summation on both the sides and divide those summations by n. So what we get? On the left hand side, you see xi's have been added and the sum is divided by n. On the right hand side, you add all the a's up to n and divide that sum by n. Also, you add all the di's up to n and divide that sum by n. Now on the left hand side, what we get? If you add this xi's and divide that sum by n, you will get x bar. That means here you get the deviation, there is a mean deviation from the origin 0. If you add a n times and you divide it by n, then you will get the a itself. And the last part, if you divide n to the sum of the deviations, these di's, and these di's are having power 1, you can see that di is actually xi minus a raised to 1. So the mean of those sum of the deviations will give you moment of order 1, and this moment is about arbitrary point. So we have given dashed here. So you got x bar equal to a plus m1 dashed, right? So you rearrange this thing and you will get m1 dash equal to x bar minus a. Now this part the first part xi minus a will be represented by di, and the second part, that is x bar minus a, will be represented by m1 dashed. I hope it's clear up to now. Okay, proceed. From 1, this equation 1, what we get? mr equal to 1 by n summation of fi. You replace this xi minus a with di, and you replace this x bar minus a with m1 dashed. Okay. Now, you change this minus sign to plus sign. So, you multiply this m1 dashed with a minus 1. Now, why we are doing that? Our intention is to go for binomial expansion. Your binomial expansion says that a and b must be added. And when raised to n, then it will give you this expression, this expansion actually, right? So, we are going for this addition sign here with a minus 1 multiplied with this second term, that is m1 dashed, okay? And this will do good, right? So, the first term, that is di, is actually analogy to a, and this minus 1 m1 dash, this whole thing will be represented as b, right? So, a plus b raised to r. Here it is n, here it is r, okay? So, you apply the binomial expansion and you get this first term. This is the first term actually. We will go for other terms here, okay? This is the first term. What you get in the first term? You see, this expansion, how it goes. The n is here, n is here, n is here, and n is here. That means power is static here, right? Now this chosen part. So this chosen part starts from 0, then it goes to 1, then it goes to 2, then it goes up to n. Now straight look at the second term, that is b part. B's power is also starting from 0, then goes to 1, then goes to 2, and then goes up to n. So this chosen part and the b's power are going hand in hand, right? They are both starting from 0 and reaches n. See the first term, that is a. It starts from n, then goes down to n minus 1, then it further goes down to n minus 2 and ultimately reaches to 0. So the a starts from n and goes towards 0, and the b starts from 0 and goes towards n, and also this chosen part also starts from 0 and goes to n, and this n part is always static, right? So this is your expression for the binomial expansion, right? So this first term is like this, RC0, the first term is di, so di raised to r, that is here it is written n, you can write it n minus 0 actually, because of all our term will be n minus 1, n minus 2, n minus 3 like that, so you can write the first term as n minus 0. So that is why we have written r minus 0, that is actually r, okay? And the second term, this minus 1 dot m1 dashed, this will be raised to 0 because this b part actually starts from 0 and goes towards n, right? So this minus 1 raised to 0 and m1 dash raised to 0. Of course, you can write this minus inside, okay? I have written here minus 1 raised to 0 and m1 raised to 0 in a separate way, but you can write this minus m1 dash whole raised to 0, you can write like that, okay? No problem. Next term. Now RC1, previously RC0, now it is RC1. di was previously r, now it goes down to r minus 1. And the b part, that is minus 1 m1 dashed, it was 0 before, now it has gone to 1, right? Next RC2, di goes down further, that is r minus 2. And the b part, that is minus 1 m1 dashed raised to 2 from 1, okay? Next. This is the fourth term, that is RC3, di raised to r minus 3, and the b part, minus 1 m1 dashed goes to 3. This is the fifth term, RC4, di raised to r minus 4, minus 1 m1 dashed to 4. You give a dot dot dot, and you write like this, that RCr minus 1, because this is the second last term, okay? So this is the second last term. After that, there will be a last term and the bracket will be closed, okay? So this is the second last term. See, r is there as it is. So RC. If this is the second last term, then after this term, this RC will reach to R, right? So since this is the second last term, that is before the last term, so this part, this chosen part is R minus 1. So that the next term, that is the final term, will be R, right? Now this first term, di, has reached 1 because in the last term, it will reach 0. Clear? And the B part, this is also the same thing. This is R minus 1 because the last term will be R. Okay? So this is the last term. RCR, it has reached R. Di has reached 0. And the B part, that is minus 1 M1 dash, has reached R. Okay? Now this expression will include pluses and minuses between them, alternatively. And which one will be plus and which one will be minus, that will be decided by this minus 1 raised to this power. That means whenever this minus 1 will be raised to even power, then it will add a plus sign. And whenever this minus 1 will be raised to odd power, then the minus sign will come in front of the term. Right? So let us see how it works. See, the first term. This one is our first term. Okay? This one. In the first term, RC0. That means RC0. This will give you this 1. Di raised to R. Alright. Minus 1 raised to 0. This part will give you 1. And M1 dash raised to 0 will also give you 1. So first term is over. Go for the second term. Second term is here. RC1. Di raised to R minus 1. And now you see, minus 1 raised to 1. So this is an odd power. So a minus sign will come in front because minus 1 raised to 1 is a minus 1. Okay. So minus 1, minus is here. So M1 dash just as it is raised to 1. Go for the third term. Third term is here. So RC2, Di raised to R minus 2, and this minus 1 now squared. That means it's an even number. That is an even power. So a plus sign is here. Okay. So you can see that this minus 1 is actually deciding whether there will be a plus sign or a minus sign in front of the term. Right? So the fourth one is like this. In the fourth one you see minus 1 whole cube. That is why minus is here. And the rest of the thing you already understand what is going on. Fifth term also you can understand. Minus 1 raised to 4. That is plus sign here. And give a dot dot dot. And then this is the second last term. This is the second last term. And in the second last term, we do nothing because we do not know actually the value of R. So if the R is 10, then this second last term will be minus 1 raised to 9. And if the R is, in that case, a minus sign will be in front. And if the R is 11, then this R minus 1 will be 10. In that case, the minus 1 raised to 10 will give you a plus sign. So that is why we do not know actually the value of R. So we keep this expression as it is. Okay. And this is the last term. In the last term, this RCR will give you 1. This Di raised to 0 will also give you 1. And this one goes as it is. Right. So up till now, we have got this expression. I will go to the next slide and I will just copy this expression and up till now what we have got. Okay. So here we go. We simplify this part, the first term, and also we will do one thing. We will open this third bracket, okay, this block, okay, so that this summation as well as this Fi gets attached to each term, okay. So we get this 1 by n summation of I equal to 1 to n Fi dot this first expression, okay, this first expression. So this first expression will give you Di raised to R, so it will look like this. Go for the second one. The RC1 has nothing to do with the summation business. So RC1 is there as it is. On the right hand side you see that's M1 dashed. It has also nothing to do with the summation business. So it is there as it is. So summation actually will work with this Di raised to R minus 1 part. So 1 by n summation of I equal to 1 to n Fi dot Di raised to R minus 1. That means the summation starts from here and ends over here. The third term you see, RC2 is there as it is. m1 dash whole square is here, and here you go, di raised to r minus 2. You see, the summation and this calculation of mean of those summations will be here. Okay. The same thing goes with this. This RC3 will be here, and this di raised to r minus 3. So it starts from here and ends over here, and this m1 dashed whole cube will be here. The fifth term, RC4 is here. The summation starts from here and ends over here, and m1 dash whole 4 will be here, right? So give this dot dot dot, and this is the second last term, RCR minus 1, RCR minus 1. This di is alone here, which will be attached to this summation. So the summation starts from here and ends over here actually. Okay, this part is not there, right? And this minus 1 raised to r minus 1 and m1 dash raised to r minus 1. And this is the last part, minus 1 raised to r and m1 dash raised to r, and there is no summation at all in the last term. Okay. So please remember that we represented this xi minus a with di, right? So this one, this di is actually this xi minus a, right? So you have this xi minus a raised to r, isn't it? Or this di raised to r. So you can say that this is a moment of order r. So you have written m suffix r. And this is minus a. That means you are dealing with a deviation about arbitrary point. That is why the dashed sign is here. So that is why we have written mr dashed for this expression. Okay. We go to the next term, RC1, and then you see that fi dot di raised to r minus 1. So di raised to r minus 1 means this deviation is also about arbitrary point, because this di is actually xi minus a, and the power is r minus 1. So this moment is actually about arbitrary point, so that is why dashed sign is here, and the moment is of order r minus 1. You see the power r minus 1. So we have written r minus 1 here. Next, you go for RC2, the same thing goes, di raised to r minus 2, so m dashed r minus 2, sorry, m r minus 2 dashed, and m1 dashed whole square. Next, this term is the fourth term, this term is the fifth term, and this one is the second last term. And in the second last term, you see that this di is alone here, this di is alone, and the power is 1. That is why we have written m1 dashed, because it is a moment of order 1, and since it is a moment about arbitrary point, we have written m1 dashed. Okay, and the rest thing goes as it is, and the last term is minus 1 raised to r this. Okay, so I hope it's clear actually how you have got this relation. So I will write it in a single line in the next slide. Okay, so here we go, mr equal to this mr dashed and rc1, mr minus 1 dashed, m1 dashed, like this what we have got, and this is the last term, right? So we have got a relation or the expression between the moments about mean on the left hand side and the moments about arbitrary point on the right hand side. And also this relation handles the order r between these two types of moments. Okay, so let us see how it works when the r's value is 2, 3 and 4. Let us start with r equal to 2. We have this r, that is mr, on the left hand side is m2, and the right hand side you have m2 dashed, rc1, mr minus 1 dashed, m1 dashed. So replace the r with 2, so 2c1, m2 minus 1 dashed and m1 dashed. This is the second term, and this is the third term, 2c2, m2 minus 2 dashed and m1 dashed whole square. Now this is the last term, because our binomial expansion says that if you have the power n, then you will have n plus 1 terms in your expansion. So you have the power 2, So that is why we have 3 terms, right? Now, it goes like this. This m2 minus 1 dashed becomes m1 dashed. And here, in the third term, m0 dashed is here, right? This part. Next, 2c1 will give you 2. m1 dashed dot m1 dashed will give you m1 dashed whole square. And this 2c2 will give you 1. This part. And this m0 dashed, that means the moment about arbitrary point of order 0. And this moment about order 0 will give you 1, we have seen in the previous session. And this m1 dashed whole square will be there. So, we got like this, minus 2 m1 dashed whole square plus m1 dashed whole square. So, you evaluate this thing, you minimize this thing, and you get m2 dashed minus m1 dashed whole square. Let's go with r equal to 3. So m3 dashed, then 3c1, m31 dashed, m1 dashed, 3c2, m3 minus 2 dashed, m1 dashed whole square, and 3c3, this is this. Now you see that r equal to 3, so we have 4 terms. So this is the first term, this is the second term, this is the third term, and this is the fourth term, right? So m3 dashed, this 3c1 will give you 3, m2 dashed will be here, and m1 dashed will be here. This becomes m2 dashed, and this one becomes m1 dashed. Now 3c2 will give you 3, m3 minus 2 dashed will give you m1 dashed, and m1 dashed whole square. In the last term, 3c3 will give you 1, and m3 minus 3 dashed will give you m0 dashed, and m1 dashed will give you. So this one goes. Here m1 dashed dot m1 dashed whole square will give you m1 dashed whole cube, and here it will be minus m1 dashed whole cube because m0 dashed will give you 1. So you go like this and you minimize this one, this 3 m1 dashed whole cube minus m1 dashed whole cube will give you 2 m1 dashed whole cube, right? Now we go with r equal to 4. m4 dashed just like before, then 4c1, this m4 minus 1 dashed, m1 dashed, 4c2, this part, 4c3 and 4c4. I hope you can understand now how this expansion is going on. So you just evaluate m4 dashed, this 4c1 will give you 4, this m4 minus 1 dashed will give you this, and this will come here, right? So this part is over. The third term, 4c2 will give you 6. This part, m2 dashed and m1 dashed whole square. Next, we go for the fourth term. 4c3 will give you 4 again. This one will be m1 dashed and this one will be m1 dashed whole cube. And the last term, this 4c4 will give you 1. And this one is m0 dashed and m1 dashed whole to the power 4. And next we go like this, m4 dashed minus this. And this one also will remain as it is. And here we can go for this minus 4 m1 dashed raised to 4. These two can be multiplied. And this part will remain as m1 dashed raised to 4 because this m0 raised to 4 will give you 1. So these three will remain same. Here you can minimize this. Minus 4 m1 dashed raised to 4, m1 dashed raised to 4, and it will give you minus 3 m1 dashed raised to 4. So this is your final expression for this m4 when you put this r equal to 4. So this is a summary you have got. This is r equal to 2, this is for r equal to 3, and this is for r equal to 4. I hope it's clear to you how the relation can be established between the moments about mean and moments about arbitrary point. If you have any kind of question regarding these reductions, you can write in the comment box. In the next video, we will talk about the effect of change of origin and scale on moments. That means when you change the origin and scale, then what will be the effect on the moments? We will meet in the next video.